Okay, I'm going to skip over this question actually and come back to it in a little while because I want to go to this question, which a lot of people had trouble with. This question refers to the daughter isotope that is formed. And notice in this graph on the right-hand side, as the amount of parent isotope decreases, the amount of daughter isotope increases because every atom of the parent isotope that decays turns into the daughter isotope. And so there's a one-to-one correspondence. There's always the same number of atoms. It's just that increasingly fewer and fewer of them are the parent and more of them are the daughter. So in this question, after one half-life, what fraction of the original parent isotope is now the daughter? And you're actually given some instructions here. Calculate how much parent is left after one half-life. And so we know that that is, if we start with 1, we divide that by 2, and that equals, of course, 1/2. And that is the parent after one half-life. Okay? How much of that has turned into the daughter? Well, then we can say 1, oops, let's hit enter. That won't let us do that. 1 minus 1/2 equals, of course, 1/2. And I know this is very easy to do this in your head, but it's important to do that because we're going to do the same kind of thing in a couple more cases where the answer will not be quite so obvious. So that is now the daughter. Now this is a realistic example of what we often do in real radiometric dating. We may not know how much of the parent we started with, but we know how much of the parent we have now, and we know how much of the daughter is. And so by getting, as it says here, the daughter isotope to parent isotope ratio, we can figure out how many half-lives have elapsed. And we know that, as we see here, the parent is 1/2, the daughter is 1/2. So the daughter to parent ratio is 1/2 to 1/2. Okay. If we want to simplify that, that would be 1 to 1. And you could use a colon here, or you could use the slash showing a division. So you could also have said 1 to 1 like that. Oops. 1 to 1. Either of those is acceptable. Okay. Let's go to question 13. After 2 half-lives, assume that every atom of the original isotope that has decayed has turned into the daughter isotope. You're going to do the same thing. So what did we do here? The first thing we did is we calculated how much parent is left after one half-life. Well, here we're going to calculate how much parent is left after 2 half-lives. So after one half-life, we have 1/2. And after a second half-life, we're again going to divide that by 2. So that's going to be 1/4. And so that's the amount of parent. So the amount of daughter is going to be 1 minus 1/4 is going to be 3/4. And that's the daughter. Okay. So we now have 3/4 daughter and 1/4 parent. So when we get the ratio of the daughter to parent, that's going to be 3/4 to 1/4. And I think it's pretty clear if you just cancel the 4's out in the bottom, that one and that one, that's going to give you a 3 to 1 daughter to parent ratio. Let's do it now for 3 half-lives. After 3 half-lives, we no longer have a half parent, or even a quarter parent, we have 1/4 divided by 2 equals 1/8, and that's the parent. And that means that the daughter is now everything else. So 1 minus 1/8 is 7/8. And so the daughter is 7/8. So that means that the ratio of the daughter to parent is now 7/8 to 1/8. And again, simplifying, that's going to be 7 to 1. Okay? Is that clear to everybody? So notice that what's happening as time goes on is that the daughter-to-parent ratio increases as the amount of parent decreases and the amount of daughter isotope increases. And you may notice that in each one of these cases, we have, if you take 7 plus 1, that's 8, we had 1/8. If you have 3 plus 1, that's 4, we had 1/4. If we had 1 plus 1, that's 2, and we had 1/2. So there is some logic to this. Okay? Okay, I'm going to stop that, and the next thing we're going to do is see if we can start applying this information.